All right. Oh, right on a level change. So this game, if you haven't seen it, let me paste the link again for those of y'all who just showed up recently. So this game, I'm on the wrong screen now. So this is a game I made. I actually had students. I believe it was the first iteration of the new 1.16. Students actually did quite a bit of this app. I gave them some structure for it and built quite a bit of this app as their homework assignments. So this is old 1.16 content here. This is a game where we're trying to storm this base. I call this a tower offense game just because I wanted to build something different, something that is a little different than anything that's out there. And our goal is to attack this yellow square, which is the enemy base. Ooh, I almost got hit there. Which is the enemy base, and then once we deal enough damage, we'll move on to the next level. This is actually the last level of the game, so once we beat this, it'll wrap around back to the first level, and we'll start over at the beginning. A few things to note here. The blue dots are all of us, except the yellow one is, of course, the one you're controlling. So there's a way to tell which character is your own. Not all of the blue dots are humans. Some of them, you can tell the ones that are just on a fixed path that always move the same exact way. Those ones are going to be AI controlled. So there are AI controllers finding their way to that base from their current position, and they'll navigate that path to find where they're going to go. That's actually part of homework 5, the next homework, enemy AI. Part of that enemy, I knew I timed that off. The enemy AI is going to do that pathfinding. We're actually going to use graphs and breadth first search to be able to find those paths and navigate those paths. That'll be probably LT 5 and 6 of the next assignment. Oh, the server doesn't like this. And you can see somebody over there is being clever and just opening a whole bunch of tabs to get a whole bunch of characters that are just dead and just not moving. But and then the towers themselves, those are aiming actually with a genetic algorithm. Homework, I was right. Homework 4. I was right the first time. Homework 4. I get confused. With 3.12, we have 5 homeworks, and 1.16, we have 4. And I know we're on the last one in each course, and I just forgot which one had 4 and which one had 5. So that's the features of this game. We're going to go to the slides, and I want to explain how the architecture of this game works, how this game actually is laid out in the code. We're not going to go through the code. There's a lot of it. It would take more than a lecture just to talk about the code. But I do want to explain the architecture and at a high level how this is implemented. Man, it really doesn't we don't even have much load on this. I'm surprised it's stuttering like that. Need to get more performant. I mean, it is coded. It is, well, we'll talk about it when we talk about the architecture. Let's get to the next level at least. Yay, go us. Then this is level 1, so this is going to be pretty easy for us all to destroy when there are this many players. We'll be done with that quick. So let's go to the slides and see how you would build something like this, or any idea that you have. You have an idea, you want to build an app, you want to build, in general, an MMO. That was the course project for the first iteration of the new 1.16. I did cut it because it was a bit much. But building an MMO where we can have multiple multiplayer games that can scale up to any number of players, as long as you have the hardware on the server side to handle that many players, scale up to any number of players, and we can all play simultaneously. That's the idea. This is an example of such an MMO, and that was the group project before, was build an MMO of your own design. So I'm not forcing you to do that anymore. But how would you do that? That's what we want to talk about today. If you want to build an MMO of your own design, how are you going to do that? So let's talk. Oh, and I call this towers. You can see it in the tab here. If I can even click the right thing. So let's talk about how this is structured in each. Let's play this all lecture. Go for it. Obviously, I got to do the slides, so I'll be in slides. You won't be on stream the whole time. Oh, all right. So an MMO, a massive multiplayer online app, in case you haven't heard this acronym before, where we can have many, many users interacting with each other simultaneously. It's usually a game, often RPGs. So you hear Mamorpaga, I think people try to pronounce it, but MMORPG. That's probably the most common one, but that we call an MMO. But any time where a lot of users are interacting online, I'll call that an MMO app. So, for example, Twitch chat right now, that I would consider that an MMO app because you have a lot of players, a lot of users interacting with each other in real time. So that's what we would want. Yeah, chat is technically a condition. I would consider it an MMO, maybe just a massive multi-user online app. Would we have to call it at that point? But anyway, you get the idea. So at a very high level, this is how Towers works. This is the architecture of the Towers app, with one big piece missing that I'll talk about at the end because I wanna save that for last. Chat is an MMORPG. I mean, once you have like the channel points, it kind of is. It starts to get gamified. You know, you kind of could with the channel points and the Twitch betting, the gambling on there now. You could consider that an MMORPG. It's got RPG elements to it, right? Very few, but you know, if you made a good argument, I think you could consider that an MMORPG. Twitch chat is. So let me quickly go over the overview here, and then we'll break this down piece by piece and explain each piece as we go. So there's a web front end for this. Most of the web front end is JavaScript. There's just a little bit of HTML, just enough to set up an empty div, which is a canvas in this case. And then I'm going to use JavaScript to draw on that canvas, draw the game board as I get the state from the server. So I have a game set up here, communicating with an Nginx server. We're not going to talk about Nginx in depth. I'd be happy to do it like after a lecture if there's enough interest. But Nginx, what it's going to do for us is serve the HTML and JavaScript files. I don't have any CSS on this app. And that's going to replace just opening the HTML file. Like when you test this locally, you'll run the server. Like the final example that we showed today, which you actually ran earlier in the semester, is to run the server and then manually open up the HTML. Nginx is replacing that manually opening up the HTML with a web server to actually serve it over the internet using HTTP. So Nginx is going to serve the HTML and CSS so we can actually get that in our browser. And then also connect WebSockets, which the WebSocket connections, Nginx is just going to forward to our WebSocket server, which is what we talked about on Wednesday. That's going to be a WebSocket server written in Scala. And then our Nginx is just going to be a liaison. It's going to get requests from our browser and just say, oh, this is a WebSocket request. This is made for Scala. I'm going to send that over to Scala. Once we're in the world of Scala, the WebSocket server is going to act as a controller in our MVC architecture. It's going to be a controller that takes user inputs, processes them, converts them into actor messages, and then communicates with a game actor, which controls the state of the game and everything that's happening in the game. It's going to send actor messages to the game actor. The game actor is going to be the model, including the tower actors. This is going to be the model of the game that controls the state of the game. It controls all the data of the game, absolutely everything. And then these actor messages are used to say, hey, this user is taking this action, which is strictly movement in this game. This user wants to move here. This user wants to move here. This user wants to move here. The game actor takes all that data, updates the state of the game, and then it's going to send the state of the game to the WebSocket server, which sends it to Nginx, which sends it to the user. So you can see the current state of the game, and that's visualized up here in the view. Each tower in the game is running on a separate actor, so each tower is acting independently of each other and independently of the app. So each tower can do its calculations simultaneously as the game is running. And the big punchline, and again, we'll go over all this slower through all of the slides, but each tower, if it takes a long time to compute, so the towers to do the aiming is actually using the genetic algorithm. It's using my genetic algorithm solution, which might take a while. Like it doesn't because I have it optimized, the one that's running on the server. But it could take a long time for a tower to compute its trajectory, because it will lead the player. It won't shoot at the player. It'll shoot where you're moving to. And if we have like 100 towers, we don't want all those towers taking all the CPU away from the game actor. We want the game actor to still be able to run and send the state of the game back to the users, even if the towers are taking forever to do their computations. So we do that with an actor system, and even if a tower does take forever, it doesn't stall the game. We don't drop frames because a tower is taking forever. We drop frames. The network traffic is the bottleneck in the game because there's a lot of network traffic going on. Yeah, it's running on a DigitalOcean server. It's in New York City. So it's actually being served in New York City. On a really weak machine, by the way. It's got like half a gig of RAM, I want to say. It doesn't have much for resources. It costs $5 a month, to give you an idea. So that's why you're seeing the stuttering. Is it 2 gigs? So that's why you're seeing the stuttering. I just don't have a lot of resources, a lot of hardware, and my network traffic is pretty sloppy. Not sloppy, but I'll explain. It works like Google Stadia, where everything is happening on the server side, and then we're only sending the game state to the clients. You're basically watching a video. Kobe's not happy. Yeah, the wife and kids just got home, and I got the gate up, so we can't get out. My wife will come up and let him free. I don't have it to understand technology. I have a boomer brain. Well, Doggo wants screen time. Wife reveal. No. Free Stadia. So let's break this down one piece at a time. You know what? I probably already said everything in that first slide. So I'm just going to say everything again, but slower. Oh, Kobe. He'll be fine. He's fine. Free Kobe. Kobe, you're fine. See, he's fine. So everything that you see is in the browser. If you inspect... Actually, let me do that. That might be worth it. If you inspect what's going on here, there should only be a couple of requests here. One for the HTML, which is almost nothing. The biggest, most important thing here is the empty canvas. I said div earlier, I meant canvas. The empty canvas, I said div that I'm using for a canvas. That doesn't make sense. The empty canvas and the JavaScript that I'm using and the Socket.io library. And that's about it. This is one of the simplest HTML files you're going to see. The library, this I didn't write. I'm just using the Socket.io library. The 2 JavaScript files, this is where a lot of the action happens. The controller, which is taking your user inputs and sending them to the server. And the view, which is taking the game state from the server and rendering it on the screen. So most of this code is to render a big old JSON object that the screen is sending you and rendering it onto the screen with all the visuals. So how is a tower drawn, for example? That's all in here. How do we get the player, like your circle, to be a different color than everybody else's circle? Well, we're going to check the ID of the socket and then choose a different color based on that ID. I'm going to close that because I'm pretty sure that's something inappropriate being drawn. Somebody's got to ruin it for everybody every friggin' time. So that's what you're seeing in the front end. So that's what you're seeing in the front end is the HTML, JavaScript, and then the Nginx server is serving those 4 files. Serving those 4 files and also establishing the WebSocket connection. So the one connection I didn't click was the WebSocket. And that's going to communicate. You're going to send messages whenever you're moving around. And you're actually going to send your key states if you look through that code. Kobe. Enough. Or really, Amy. Come get him. And that's what you're going to see. And then the WebSockets, you're going to send your key states, so which keys are currently being pressed down, to the server. And the server is going to send over the WebSocket the whole state of the game. On the next step, the web server for the WebSockets is, like I said, just a liaison. It's going to take your messages, your WebSocket messages, and forward them either an HTTP request and just serve those static files, or it's a WebSocket connection, and it's going to forward that information to the WebSocket server. So there are 3 different events that can occur. All right. Oops. Such a whining dog. Go. The dog cries so much. Every little thing that happens in his life, he's got to cry about it. Yeah, he's gone. He's spoiled, is what he is. So you're going to forward all this stuff. There's 3 different message types that the WebSocket server is concerned about: when you connect, when you disconnect, and whenever your key state changes. So whenever you press or release a key, it's going to be a new WebSocket message that's forwarded to the WebSocket server. The WebSocket server is going to send the entire game state in a giant JSON object once every 10th of a second. So we're running at 10 frames per second in the game, which is adjustable. I can set that to 60 if I want. It's just a lot more network traffic to be able to get that. So the front end is very, very dumb. It doesn't do anything. It doesn't compute anything. And all the actual computation is on the back end. And when you change your key states, the back end is getting that change from all the players and then processing that information. And then you don't actually see that change. If you hit the left key, you actually don't see yourself move until all of the network traffic resolves and you get that next 10th of a second update. And then the server will say, okay, your new position is here. I've calculated your velocity and your direction, it's included in velocity. But I calculated your velocity, this much time has elapsed, your new position is here. 10th of a second later, okay, your new position is here, etc. That's all I need to say there. And then everything here in this green box is Scala. This is the Scala world. Nginx is a separate service. This is a separate piece of software that you'll download, install on your machine if you want to use Nginx. The browser, this is across the internet right here. The browser is running on your machine, wherever you are. And then the rest of Scala, this is all running, and the web Nginx actually, this is all running in New York City, on my DigitalOcean server. So all of this here is Scala. This is where we enter the world of Scala, and this is the code where you should have a pretty good grasp on. You should be able to understand if I share it. Again, I'm not sharing this code because it has the solutions to multiple assignments that are still being used, including some solutions for Homework 4, which isn't even released yet. So I can't release the code for this, unfortunately. But, oops, that should say WebSocket Server. So the Scala program runs, and the entry point to the outside world is a WebSocket server, not a TCP socket server. It actually used to be a TCP socket server in the first iteration of the new 1.16. We don't do TCP sockets anymore in 1.16. This should say WebSocket server. That's multiple times I missed that in the slide the last few semesters. And creates all the actors. So we run the program. The program's going to start the server in one actor, start the game in another actor, and then each tower in its own actor as well. And then all these actors can communicate with each other across these arrows. Like a tower never talks to the WebSocket server. I guess that's the only thing on screen right now. The game actor never talks to the web server, etc. But through these arrows, that's where all the communication is going to happen. Across all these things that are running concurrently. Like each box is running concurrently. And then the arrows are the boxes that communicate with each other. Yo, what's up, Trino? So the WebSocket server is this is our an actor that's gonna start up, fire up the WebSocket server, and listen for connections on port 8080 like we've seen on Wednesday. WebSocket server is going to receive your key states as a JSON string. So our WebSocket server, we only set them up to listen to string messages. So it's going to listen for a message of type key states that has a string, which is going to be a JSON string, which tells me which keys you have pressed down. Up, left, right, down. Which ones of those are down? Which ones of those are up? Do I move you diagonally if two of those are up? If you have left and right pressed, should I move you at all? It's going to get that key state and not actually do any processing. Actually, I think I might do the processing here. Yeah, I do the processing here. Take those key states and figure out which direction you should be moving in. And then convert that into an actor message to send to the game actor, where the game actor is running the entire game, all of the game logic. The WebSocket server is going to process those key states and say, send an actor message to the game actor, which is going to be an actor message. I was checking to see if I put the type of the message, which is going to be a message that says, move this player, or this player's new velocity should be this. So the game actor only cares about what your velocity should be, and it's going to expect actor messages and respond to actor messages that say, this player's velocity is now this. Their velocity vector should be to the left and up. Like that's where this player should move. Or the signal can say, if all the keys are up, say, this player should stop. That's what the game actor is listening for. Those are the messages that it's receiving here, is which direction is this player currently moving in. The game actor does not care about the key states. That's being processed in the controller, because the game actor doesn't give a crap that you're pressing keys down. It just cares what direction you intend to go. So it gets your intended velocity. What direction are you trying to move in? That's the actor messages that's receiving from the WebSocket server. And it's going to send the game state to the WebSocket server. I feel like I said that like 3 times. I'm going to stop repeating that one. The game actor maintains the entire game. And then I have 30 FPS right in here. But it's going to be... Oh, actually, yeah. I didn't... the physics. The physics is going to run. So since we're concurrent, game actor is listening for quite a few different actor messages. 2 of those actor messages are update the physics of the game. Take all the velocities of all the players and all of the projectiles that the towers are shooting and all the AI players. Take all of those velocities and update them based on some DT. So every 30th of a second, let's update the physics of the game based on everybody's intended velocity, and then do collision detections. Are they moving into a wall? Because we don't want to move them into a wall. What should happen is a projectile hitting a player currently? If so, move that player back to the start and destroy that projectile. So all of the physics logic is happening in the game actor class, and that's being updated at 30 FPS. There's another message that it's responding to, which is the, hey, broadcast all of this, all the information that you have, the entire state of the game, to all of the users, which it's going to process a giant JSON string saying all of the locations of all of the players, send that to the WebSocket server. The WebSocket server is going to broadcast that through Nginx to all of the connected players so they can get the state of the game. That one's running at 10 FPS. So we have 2 different loops. Our physics loop, which can run faster because it's all, in our case here, because it's all local. And then our update loop, which is sending the state of the game to all the players, which we're running a little bit slower just because we have network delays. We don't want to flood the network. We don't want to saturate our network connection. And even then, that's pretty big. And this is working like Google Stadia, where nothing is really happening up here. You're just sending your user inputs to the backend. The backend processes everything and effectively sends you a video of the game that you're playing. In Google Stadia, it's pretty literally like a video, watching a video. And in our case, we're sending the game state and letting the front end render that information. So the game actor has no clue that any of this exists. or really the WebSocket server. It's not aware of any of that. All the game actor knows is that it's receiving actor messages. It's receiving messages. There's a case class of intended velocity. It's receiving those actor messages and then processing them. It does not care where those actors came from. In fact, it doesn't even know that it's part of an actor system. There's a game actor that's a layer in front of the actual game itself. So we can take this game and put it in a non-actor system. We can put it in a system that's not part of a WebSocket server. We can put it in a system that's not even a web app. And that's what we want from our code. We want it to be nice and portable. And we saw this in point of sale as well. Your point of sale, your checkout machine, your self-checkout class, that can be used in a lot of different applications. We used it as a desktop app with a GUI, but you could easily turn that into a web app without changing any of the code that you wrote for that assignment. Everything you wrote is completely portable. You just replace the view, replace the controller. You can turn that into a web app. You can even embed it in an actual self-checkout machine. You can use that very code, the same code that you wrote in a real self-checkout machine. So we want to take that same principle here. The game itself is completely independent of any of these other parts. It's completely independent of the fact that it's a web app. And we could build a desktop GUI and have a desktop GUI maybe over here that communicates to the WebSocket server and have those players able to play the same game with the same players and interact with the web front end, much like we did with the chat app last time. And then the tower actors. The game actor is going to create a tower actor for each tower. It'll destroy those tower actors each time the level changes and then create new tower actors for each level. So we can control like the number of actors even in this system. So we'll create a tower actor for each tower, and they're going to do their own thing. We're going to send them once a second a message that says, hey, fire. Actually, they send that themselves, now that I think about it, but it's irrelevant. Once a second, they get a message that says, hey, fire. It's going to do all its computations, and then send an actor message to the game actor, which says, add this projectile to the game with this velocity at this location. So once the tower figures out which direction it wants to fire that projectile, it's going to let the game actor know, hey, I'm firing in this direction. Add that projectile to the game and do your thing. After that, the tower doesn't care about that projectile. The game actor takes care of the physics of that projectile. And all of that happens through actor messages, so the tower can be completely independent of the actual game. The game is going to give, the tower is going to ask the game, hey, what's the current state of the game? It gets the state of the game, processes that, and says, okay, I want to fire here based on this current state, gives that to the game actor. If the tower is slow doing that computation, it's going to miss the players by a little bit. The tower is fast enough, it's going to hit the player, which they do, of course, as you know from playing it. Towers Game of the Year. So with this architecture, I'll take a quick breather here. And with this architecture, first of all, does that make sense? Do you have questions about it? And second, how do we add AI to this game? So there are AI characters, we know that. How would we add that to this architecture to get AI to work, given this model that we have? You missed the doggo arc. Yeah, you could have two games running at the same time. So if you want like a lobby, if you want multiple lobbies for the game, we would create more game actors and then keep track of each WebSocket connection. We would keep track of which game they're currently in and then only send their actor messages to that game actor. And then when we get messages from a game actor, we would only forward those to the players in that lobby. So we could easily expand this to multiple games. We would add a main lobby actor, which would control all that stuff, control all the games. Easy peasy. Not easy peasy, you know, there's a little bit of work to do, but it's not like it's a complete rewrite of everything that we've done. It's easy to expand. That's what we want from all our code. Any code you write, that's one huge thing you want. Easy to change, easy to expand, easy to add new features like this. Adding AI. When we add AI, we shouldn't have to change anything with our architecture here. If we don't have to change anything with our architecture to add new features, then we got a good architecture there. Now, if we did something like wrote all of this code in one big blob of of a class or an object, and it was all mixed together and intertwined and non-concurrent and just a big old mess, it's going to be really hard to add AI, and we're probably going to have to refactor our code, move everything around, reorganize things to try to get AI in there. It's going to be a real pain. We're going to add AI without changing any of this. Absolutely nothing is going to change from this diagram. That's what we want. Import AI. Yeah, exactly. So for AI, we're going to add an AI controller. So I can control like how many AI. My AI controller says like add an AI to the game. I want to say it's like 7 right now. So there's a constant in AI controller that says like 7, and the AI controller is going to create an AI actor for each one of those AI. The AI actor is going to receive, through these arrows, is going to receive the state of the game. That actor is going to look for the goal and move towards it while avoiding walls. It's effectively a maze solver. Move towards the goal while avoiding walls. It will not avoid towers. They will move right through towers. They're not that smart. They're not that clever. They're just looking for the goal and moving towards it, and that's it. That's what these AI do. Whenever they want to move, whenever an AI wants to move, they decide, I want to move in that direction. What they do is send an actor message. They actually go through the AI controller, but they send an actor message to the game actor. That's the same exact message type that comes from the WebSocket server that says, this player wants to move in this direction. Same exact thing when a player hits some keys, goes through Nginx, the WebSocket server processes those keys and then says, hey, game actor, this player wants to move in this direction. Same thing. AI, this part is different. AI looks at the state of the game, decides where it wants to move, and tells the game actor, this player wants to move in this direction, with the same exact message, to the point where the game actor doesn't even know or care whether a player is an AI player or a live human player accessing this over the internet, or if it's a live human player using a desktop app, which I never built, but we could build a desktop app for this. The game actor doesn't care. Its API just says, tell me the player ID and tell me where they want to move. And that's it. So nothing at all changed here, except like one line of code that says, actor system, add this AI controller to the actor system. That's the only code that changes. And then all this is brand new code, which doesn't interfere and doesn't require rewrites anywhere over here. Are there any questions? Y'all could just code this up tonight, right? Is Towers open source? No, I just said that. No, Towers isn't open source because it contains the solutions to a lot of homeworks that we use in 116, including part of homework 4 this semester that you'll see. Yeah, I like the confidence out, y'all. 10 minutes max. Speed run time. This has the solution to genetic algorithm, and Towers use genetic algorithm. The game actor uses physics engine, which I didn't run in this section this semester. But the solution to physics engine. AI controller has pathfinding using graphs and breadth first search. There's just solutions all over the place here. I used those 3. I want to say 4. I'm blanking on what any other ones are, though. But at least 3 homework solutions went into building this. Which I do to emphasize that the solutions that you write for the homeworks, those aren't just isolated things that you write and they're just one and done and then you throw them away. They are useful. They can actually be used, and they're designed to be able to be used in other programs. You can take your genetic algorithm and apply it to something else. I'm using the genetic algorithm for the towers to figure out where to shoot because I didn't feel like doing the math and the physics to figure out exactly how to lead a player based on their velocity to hit them. I just came up with a cost function and an incubator, threw it at the genetic algorithm, and let the genetic algorithm optimize it. Done. Goes to New York to steal the server. I don't know if that'd be worth it. Plus you gotta get through DigitalOcean security. Next UB Hackathon Towers too. Alright, So Towers is pretty intense. There's a lot going on there, so much so that I'm not going to go through the code. But let's look at something quite a bit simpler. And I want I hesitate to call it a game, an MMO. I'm hesitant to even call it that, but an app, I'll say, where you can move your mouse around the app, and other users can see your mouse move. Not particularly fun, but hey, let's do it. I'm going to call this a proof of concept because it's going to prove that we can build an MMO. So let me show this. The server's not running. Let me run the server. And this one I will go through the code for. MMO server. Let me move things around. Let me run this. So I'm going to run the server. This is in the examples repo under MMO. I'm going to run the server, and I'm going to open this HTML file in my browser. I already have that open, so I'm not going to open it again because I already have this set up the way I want. And when I'm in the browser and moving this around, everybody else who's connected can see this move around. This isn't hosted on the internet, so you can't play this one and all see your mouses move around. But you can see I have two windows open, and they can see each other move around. So this is a proof of concept that we could build an MMO with this technology. Once you can interact with each other like that, you can start building more features. You can build a UI. You can, instead of just following the mouse, you can click and then have your player move to that location. You can click to attack, things like that. Here I have the WebSocket connection open. Let me refresh this actually. Let me not preserve log. Come on. And we can actually see the WebSocket connections. Look at all these messages we're getting. It's a lot. Let me move around a little bit. And we can see that we're sending the current location of our mouse pointer. And then 10 times a second, we're getting the location of all the mouse pointers. All right, so that's the app. Much simpler than Towers. We'll actually be able to get through all of the code. So let's do that. Let's do exactly that. And that's a lot of game state messages. You can do the same thing with Towers. If you inspect element and go to the WebSocket, it's a lot of network traffic. It's a lot. That's what makes the game choppy, is sending so many messages. So let's dissect this. Let's start at the HTML because there's not much going on here. Just like Towers, not a whole lot. I have a canvas. I'm doing style cursor none. So when you're hovering over the canvas, your cursor disappears, and your cursor is your character in this game. I'm pulling the Socket.io library. In Towers, I'm self-hosting it. That's why the URL looked different. Here, I'm getting it from the CDN. And then I'm grabbing my view and controller, my JavaScript code. The controller is going to grab my mouse movements. Every time the mouse moves on the canvas, I'm listening for the mouse move event, and then calling this function every time my mouse moves, which I can get from the event the X and Y coordinates of my mouse. And then I'm going to turn that into a JSON string and send it over the socket in a message of type location. So on the server, I need to expect a message of type location, which is a JSON string, which contains the X and Y values of that position. In the view, this is where I actually make the socket connection. That socket, it's on the page, so I have access to that socket over here as well. I make the socket connection. And when I receive the game state, I'm going to call this update function, which is going to read the game state, which is the location of every player. And I'm going to add a rectangle. Oh, that's clearing the whole canvas. I'm going to add a rectangle or a square. I'm going to add a square for each player in the game state. I'm going to read their XY position and put that player there. And then based on the ID of that player, if that player equals my ID, I want to make that player a different color just so I can distinguish who I am. I want to see which one is me. And then draw that rectangle, or draw that square. And the rest is setting up the canvas. This is similar to the GUIs we did in. These should be const. Yeah, it doesn't. I'm not going to bother with that right now. Yeah, I am. This is similar to the GUI stuff we did in Scala FX. It's very similar structure to that, but we're working with an HTML canvas instead of writing on it with JavaScript instead of using Scala and Scala FX. Just different libraries because we're in different environments, but very similar. We're going to place a square as a rectangle and draw our game state. And you can see, I flashed it in the browser, but you can see all the code that's used to generate, to draw the game state in towers as well. It's just more of that. Nothing too complicated, but there's a lot of it, so it would take a while to read through all of it. So that's the front end. That's all the static files. I want to jump over to this class real quick because we'll use this in the server, and I'll save this MMO server for last. Character object. This is just going to give me a way to represent the location of a character with X and Y location, and a way to convert their location into a JSON string. Now I cut this JSON library from the course, so we won't be able to. You have to study a little bit to see how this JSON library works. But suffice to say, this is a way that we're creating JSON strings in Scala, which is pretty difficult because it's a strongly typed language. So it's harder than just saying to JSON. We have to do a little bit of work here and use inheritance and polymorphism to get that done. So we're going to return this location as a JSON string, and we're going to add the player ID in addition to the X and Y location. Message types, there's only one, a case object named update, which brings us to the server. So here we're going to use both WebSockets and actors in the same program. We did that in Towers, but I didn't get to show the code for that. So here I want to show code where we're doing both of those things. So let me start with the WebSocket stuff. The WebSocket, we're going to use that same configuration, that same setup that we used before. We're going to listen on localhost 8080. We're going to start the server. We're going to create the server and start it. And we're going to add 3 listeners. We're going to listen for connections, disconnections, and that location object that the client's sending us with the XY of their mouse position. So we're going to listen to those 3 message types. And we're also going to keep a map which is going to store the socket, a reference to the socket for each player, each connected player, and map them to a character object for their character. When a player connects, this is going to be called when a player connects, and we're going to update that map. We're going to say this socket for this player. We're going to add that to our map, so we remember this player, and we're going to initialize their position at 0, 0. So when you first start up the browser, when you first visit the page, you're going to be at position 0, 0 until you move the mouse over the canvas and start establishing an actual position. On disconnect, I'm going to remove that player from the data structure. And then when I receive a location from a player, that message is going to be a JSON string with XY. I'm going to read those values. I'm going to look up the character for this socket. So your ID is based on your socket connection. Get that character, and then set the XY position for that character to the XY from that JSON string that we just received. So this is an actor system. Oh, that's what I want to show. So MMO server extends actor. This is both a socket server, a WebSocket server, and an actor. So to set this up, to actually start the server, we're going to need to set up an actor system and create an actor of that type and add it to the system. The reason we're doing this is because we want to do something else other than the server. If we just start the server like we did on Wednesday, we're going to the server is going to control our program. We're going to run the server, and the server is our program in a very real sense. We don't want that. We want to do other stuff in addition to the server. The server is just one piece of our program. Like if you think of towers, the WebSocket server was one piece of it. Then the game was another piece that needed to also do its thing, and then the towers needed to do its thing. We don't want to roll all of that and have that all linked inherently to the WebSocket server. So we're going to disconnect those through an actor system and add the MMO server to the actor system. So then we can also do other things simultaneously just by adding other actors to the system. Now for this proof of concept, we don't add other actors, but this is where we would. We would add other actors to the system that did other things. We could add a game actor. We could add an actor for each player if we wanted. We can do whatever we want in addition to the server. For this one, we're doing just one thing. This line, this long line, is going to send the MMO server an update message every 33 milliseconds. So we're going to run at 30 frames per second, send the update message, and now since the MMO server is an actor, it extends actor, it has to implement receive. Now remember, we can do all of our class stuff. Look at all this stuff that we did inside an actor. When we have a class, we can do all our class stuff. When we extend actor, that just means that we also have to have a receive method. So never be afraid when you're writing an actor to add all your class stuff, variables, methods, all kinds of stuff in there. We have a lot of stuff in this one. Then the actor part, when we receive a message of type update, we're going to broadcast to all connected clients the game state as a big old JSON object. And the last piece of this is, which I'm not going to go into detail with, is going to our map, getting all of the players, and converting them to JSON strings and sending their ID X and XY locations as JSON strings to everybody as a message of type game state. The client is going to receive that message of type game state and then render all those squares to the browser, to the canvas. And look at that, 1 minute to spare. Look at us. Any questions on that while we're still in the YouTube video? Besides, what the hell just happened? That's probably your question. But you do have access to all this code. You can look through it a lot slower than the blistering pace I just went through it here. All of that is stuff, aside from the JSON stuff, because we didn't do that this semester. Aside from the JSON stuff, you should be able to follow everything that we just went through in this server. What is JSON? I'm going to assume that's a troll. Unless, Muffin Man, unless you didn't take 115 here. I suppose that's possible. Alright, let's end the YouTube video. Bye, YouTube.